Bismillahirrahmanirrahim. Dear students, hope you will be fine. Today we will discuss about hybridization, another important concept in organic chemistry. So before going to the definition of the hybridization, let's discuss about the background, why hybridization is needed in organic chemistry. So we have beryllium with atomic number 4, 1s2 and 2s2. We have boron with atomic number 5, 1s2, 2s2 and 2p1. And we have carbon with atomic number 6, 1s2, 2s2 and 2p2. Now on the basis of the valence electron and unpaired electron, we can say that beryllium cannot form covalent bond. Boron can only form one bond, and that is why it is univalent, while carbon can form two bonds and it can be considered as divalent. But experimentally it is proved that beryllium is divalent, boron is trivalent, and carbon is tetravalent. So this can be explained on the basis that one of the s electron of the beryllium, boron and carbon excited to the phi orbital and will gives us, for example, in the case of beryllium, we have two s and we have 2p. So this is the ground state electronic configuration. Now one of the electron will be excited to the higher p orbital, energy p orbital, and we will get this kind of electronic configuration that is called the excited state of electronic configuration. So this is the ground state and this one is the excited state. Now in this situation, beryllium can form two covalent bonds. Similarly, we can explain the boron. So with boron we have 2s electron and we have one electron in the phi. So after excitation it will gives us this kind of excited state electronic configuration, and this is the ground state. Now it can be considered as trivalent. Similarly, carbon with atomic number 6 having this kind of ground state electronic configuration, it can be converted into excited state and we have three unpaired electron, which prove that carbon is tetravalent. Now if we take the example of beryllium hydride or beryllium chloride, how we can explain the nature of bonding in beryllium hydride. So as we see that beryllium has 2 unpaired electron, one in the s and the other one is in the p. So we can say that beryllium, one of the s orbital of beryllium combined with another s orbital of hydrogen. While in another direction, we have one p orbital of beryllium combined with one s orbital of the hydrogen. So we can get BeH2. But here the bond situation is different. One of the bond is formed from the SS overlapping, while another bond is formed from the SP overlapping. And we have idea that when there is SP overlapping, we have more overlapping, more extension of overlapping, and we have stronger bond due to more extension of overlapping. While in this situation, we have less extension of overlapping, we have weak bond. But experiment shows that both of the beryllium hydrogen bonds are of same situation, of same energy, of same strength. So how this can be explained? Both beryllium hydrogen bonds are of the same strength. So this cannot be explained on the basis of only the overlapping or combination of atomic orbital of one atom element with the atomic orbital of another element. So this problem was resolved by two scientists, that are Pauling and Slater. The same situation, the same case is also with boron and carbon. So Pauling and Slater explain the nature of hybridization, and now we can define the hybridization is the mathematical the process of mathematical combination of atomic orbitals of different shapes and energies to produce a new set of hybrid orbitals of same shape and energy. Such phenomena is called hybridization. So if we apply the phenomena of hybridization to the beryllium hydride as well as the other molecules, then we can explain the nature of nature of bonding. For example, in the case of beryllium, two of the orbitals of beryllium, one is s and the other one is p orbitals, they are combined together through mathematical operations, and we will get two kinds of hybrid orbital. Now these two hybrid orbital same shape and same energy. and they will combine with the s orbital of the hydrogen and another s orbital of hydrogen. So we will get BeH, and both of the bonds are of the similar strength. So this kind of hybridization, in which one s orbital and one p orbital combined together, is called sp hybridization, or we can say diagonal hybridization. So the arrangement of these hybrid orbitals will be in such a way that the angle between the two is equal to 180, and that is why this angle is 180 degree, and the geometry of the molecule is linear. Another example is BF3. So in the case of BF3, one s orbital combined with, we already know that B in their excited state having such kind of electronic configuration. So one of the s orbital combined with two p orbitals, 2px and 2py orbital, and after mathematical combinations, they will give us such kind of geometry or shapes in which we have three hybrid orbital combined together, and that kind of hybridization is called sp2, or we can say trigonal hybridization. In trigonal hybridization, we have angle of 120. Now this kind of the three hybrid orbital of the boron will then combine with the p orbital of the fluorine, and we will get this kind of geometry, which is the trigonal geometry, trigonal planar geometry, and the hybridization is called sp2 type of hybridization. Similarly, we can explain the hybridization in methane. In case of carbon, we know that excited state of carbon 1s2, 2s1, 2px1, 2py1 and 2pz1, and now the combination of these four hybrid orbitals on carbon, we will get uh, 2s, 2px, 2py and 2pz. We will get these kind of hybrid orbitals, and this is the sp3 type of hybridization, and the angle in this situation is 109.5 degree, and this is also called tetragonal hybridization, and we can say that the angle is 109.5 and the geometry is tetragonal, and the well-known example is methane. Okay. Now there is a question arises that the hybrid orbital have more energy than atomic orbital. How to explain this query that hybrid orbital have more energy than atomic orbital? So either it make the molecule unstable or not. Hybrid orbital have more energy than favor atomic orbital. So this can be explained on the basis that initially we have hybrid orbital with more energy, but after bonding there is another energy involved, and that is the bond energy, and the bond energy in this process is always greater than the hybrid orbital energy, and the more energy of the hybrid orbital is compensated in this situation. It means that when we have atomic orbital, so before going to a pure atomic orbital having no hybridization, but when atomic orbital start to form bond, then it start to produce hybrid orbitals, and that hybrid orbital have more energy and are unstable. But after the formation of a bond, we have more bond energy release, and that is why the more hybrid orbital energy is compensated in this process. Okay. Now, how we can determine the hybridization of atom in a molecule? Hybridization, how to determine hybridization type in a molecule. So there is a general method in which we can say that the nature of the hybrid orbital, or we can say the type of hybridization is always equal to the number of groups. We can say these groups are steric number. We can give these groups as steric number, and this is the steric number is always the combination of the bonds plus lone pair. So the combination of bonds and lone pair can give us a steric number. So generally we use single bond, double bond, triple bond, lone pair. So the steric number for this single bond is 1, per double bond is 1, per triple bond is 1, and for the lone pair is 1. For example, if we want to explain the nature of the hybridization in methane, so how many steric number are there? So there are 4 bonds. So we have 4 bonds, and there is no lone pair. So the steric number of carbon in methane is 4, and when we have 4 steric number, then we have hybridization sp3, steric number 4. When we have steric number 3, we have hybridization sp2. When we have steric number 2, we have hybridization sp. Now in this situation the steric number is 4, so the hybridization is sp3. Similarly, in the case of ammonia, we can explain the nature of hybridization because we have 3 bonds and 1 lone pair, so the steric number is 4 and we have hybridization sp3. Similarly, in the example of water, we have 2 lone pair and 2 bonds, so the steric number is 4 and the nature of hybridization is sp3. We can explain different molecules with the help of this. For example, if we take the example of this formaldehyde, so what do you think about this? What is the hybridization of carbon in this molecule? So you see here that we have 2 single bond and 1 double bond, and 1 double bond is considered as one's steric number. So the total steric number for carbon is always equal to 3, which means that the hybridization is sp2. So the carbon in this situation is sp2 hybridized. So this is the sp2 hybridized orbital. While for oxygen we can also take the nature of hybridization in oxygen. So what is the nature of hybridization in oxygen? We have two lone pair and we have one double bond. So there are steric number 3 and the same kind of hybridization sp2 involved in this kind of molecule for oxygen. Another example is CH3 COH. Now there are two different kind of carbon. One is this. So what will be the hybrid or type of hybridization for this carbon? So if we count the steric number, so we have 4 bonds without lone pair. So the steric number is 4 and the hybridization is sp3. Similarly, in this situation, we have 1, 2 and 3. So the steric number is 3 and the hybridization is sp2, and the similar situation for oxygen. An example of organic molecule Okay, so this kind of molecule, we have this kind of molecule. So what will be the nature of hybridization of this nitrogen and this nitrogen? You can explain this, and I hope you will you can write the nature of hybridization for this situation, but there is some differences. For example, if we take the case of this and we apply the same rule, for example, for this nitrogen we have 3 and 4 because there is one lone pair as well. So we have 4 steric numbers. So the steric number is 4. So the possible hybridization is sp3. While similar situation is here. So the steric number is 4 and the possible hybridization is sp3, but this is not correct because of the involvement of the lone pair of the nitrogen here in conjugation, delocalization. So it is delocalized. The lone pair is delocalized throughout the ring, while in this situation the lone pair of nitrogen delocalized, conjugated with the carbonyl group. So this lone pair is not available for hybridization. So if we remove this lone pair and we will not count this pair in hybridization, then the nature of hybridization in this situation is there are 3 steric number and we have sp2 type of hybridization in this case, while here there are 3 steric number and we have sp2 type of hybridization in this. So both of the nitrogen in this case have sp2 type of hybridization because of the involvement of the lone pair of the nitrogen in the delocalization of the ring and the delocalization or conjugation with the carbonyl groups. So I hope you will understand this and you can practice different kind of problems in hybridization, and if there is any problem you can ask me. I hope you will enjoy a lot. Thank you.